All right, so let's quickly get into this. So this is MLB Performance Salary Prediction Case Study by myself, Alden Short. So a little business problem understanding. This case study uses 28,000 observations with the use of RapidMiner's auto tool to hopefully predict a player's salary based upon their hitting statistics. So let's further go into this business problem understanding part two. This data was formed to see who's the most cost-effective players from the 2013 season in the MLB. So I will be slightly using the data in a different way by trying to use all these metrics to perform a potential analysis on predicting future players and past players' salaries based upon their hitting statistics. So data understanding and collection, like I said again, this is a little bit over 28,000 observations. We can see here some of the different locations that we have some of these observations from, obviously from all 30 MLB teams. For example, Boston Red Sox, we have 1,057 observations from them, 999 from the New York Mets. So here is a little bit of information on the variables that I used on this data set. So for example, home run, the number of home runs a player hit, player name, the player's name, salary, which is obviously what we're measuring, BB, the number of base on balls the player drew, throws, the throwing handedness, so if they're left or right-handed. So here you can see these different variables that I used. So let's talk about data preparation and feature selection. So one of the first things that I had to do in order to make sure that this data was reliable and that I could use it for the auto model feature is I actually had to load it into RapidMiner. And when I loaded it and just ran it and I went to the statistics here and it shows all the statistics for the data, it showed me if there's any missing values and important things for the data that I should know to fix. And it also tells you if it's an integer or if it's nominal. So it actually told me that none of these 28 variables are missing any values. So that was a good sign. And through further visualization, I knew that I didn't actually have to do any editing on my data. I was just able actually to load it into the auto model feature. So let's go to that. So this is the model development. So for the auto model feature, you have to choose whether you want to predict, cluster, or detect outliers in your data. So obviously I want to predict player salary based on performance. So I selected the salary column and I was going now to move on to the task. So this is model development part two. And this is preparing your target. So basically, I had to tell the auto model feature here that this is not a classification issue. And basically, I had to make sure to tell them that this is not binomial. So let's move on to the selecting of the inputs. So this is a very important stage of the auto model feature. And it tells you whether it thinks these certain variables that you're using are bad or not at predicting, for example, predicting salary for me. So it actually told me that 27 out of 28 were bad, as we can, or 27 and 28 were actually good, and there was only one bad, which is index. So I went with what it suggested, and I chose to look upon salary based on these 27 different inputs. So then I have to move on, and I have to go to the model types. So I wanted to do a lot of models. I wanted to make sure I had a lot of things to compare by to get the best, most reliable model. So that's why I decided to go with the general linear model, the deep learning, the decision tree, the random forest, and the gradient boosted trees. And I didn't decide to go with the support vector machine, but these five models I went ahead with. So then it shot out my first results here. And firstly, mainly you can see the deep learning and the gradient boosted trees did take a little bit more time to make rather than the linear and these other models. So this first metrics that we see here is the relative error of these models. So we can see that the relative error for the deep learning was 52%, which is actually the lowest, which is not a good relative error score, obviously, to be 52%, which means that the true value and the predicted value were actually different 52% of the time. We can see second place here was gradient boosted trees with 55, and the highest relative error for this model was linear at 68%. So that is not good. Basically, so far the model is not doing a great job at telling us or being able to predict salary. So let's move on to a different performance metric. And one that I thought was very important was correlation. How well correlated is this data at telling us the correlation between the independent and dependent models, or independent variables. So we can see here that obviously the higher you want it to be more correlated. So the higher correlation was the deep learning model. And then again, we can see that the second highest was gradient boosted again, and that the lowest was actually decision tree and the second lowest was the general linear um, model. So we can see here again that deep learning is in the first place when it comes to a model, and this is pretty good correlation scores for this model. So the data, these models are very well correlated at telling the correlation between the independent variables. So let's move on to the RMSE. Um, so the RMSE scores here we can see are not good at all. So the lowest is 2.1 million with the deep learning. We can see that the highest is 3.1 million with the decision tree, and the second lowest is 2.6 million with the gradient boosted tree here. And that would be good if MLB player salaries were in the billions, but it is actually not in the billions. They're in the millions, and the average during this season, which the data was from, was about 2.5 million. So as you can tell, this is plus or minus the variation. This is a standard deviation of basically the whole value. So this is a horrible RMSE score, and these models do not do a good job with the standard deviation of their models at predicting true values or not. So furthermore, to give you a more clear visualization on how these different models and how they stack up against each other, I decided to do these prediction charts. So as you can see, this linear model's predictions were not able to go to what the player salaries were at all. It does not fit the data well at all. But as you can see, the gradient boosted trees was a little bit better at fitting the data. As you can see, it's kind of getting that upward right trend involved. But then you can really see that the deep learning model, which has been in first place this whole time, was able to predict quite well along, obviously with a large gap, but it was able to predict a lot better than the gradient boosted and the linear model here. So the model results in communications. So basically, due to all of this, I decided to go with the deep learning model, and I put some key performance metrics here. Some I've talked about, some I have not. That basically decided why I was able to select the deep learning model and not another model for analysis and interpretation, because it had the lowest RMSE, the highest correlation, the lowest squared error, and the lowest absolute error, which decided to make me pick it. So let's move on to some model results of communication. So I went on to look at the correlation between the inputs and outputs and their weight. So as we can see here, some weights that have high significance. So basically what this means is this input of season, as we can see, has more effect on the output, which is salary for these players. So we can see that the season here has one of the higher weights here at 0.3, and we can see home run, RB, BB, and R are very highly they're very highly weighted because they have more effect on the output. And then in comparison here, we can see some of these lower inputs that have no to little effect on the output, which is, as you can see, throws, SH, league, and bats. They have little to no effect on the output. So moving on to some more model results in communication part 3. Here's some other key metrics that I used to describe the model and how well it does at predicting salary. So basically, MSE here, it measures the overall amount of error in the model, and it does this by averaging the differences between the predicted and true values. And as you can tell, this is a very large number, being e to the 12. So basically, this tells you the difference between the predicted and the true values is very far, and this model doesn't do a great job of doing that. Then again, the RMSE does, which I've already talked about, is very similar to that as well. Obviously, closer to 0 the better. The model of this has a 1.6 million RMSE, which is not good, but it was the lowest RMSE score out of all the 5 different models. And then, believe it or not, the correlation, the R2 for this, which is the correlation between how correlated the dependent variables are to the independent variable. So 77% of the variation in what we are measuring, salary, is caused by the inputs that we are measuring. So this is pretty good, 77%, that's a pretty high number, and we like that. So the mean absolute error here is actually very interesting. This is the numerical value between the predicted and the true, and we can say that's almost a difference of $1 million, which is ridiculous. So this model is not doing very well job of helping us predict salary, at a very high rate or at a certain standard. So model deployment, some main things for model deployment that I thought about this. This model would obviously have to be edited to be more accurate. And this could be done potentially through new variables or existing old variables. So this model obviously have to be fixed, like I said. And once it was fixed, I think this model could be deployed to baseball players and team owners themselves. So a team owner could say, hey, I don't want to keep paying you this much unless you get your performance metrics up because, hey, most people are getting paid if they have these stats this number, but you want to get paid this number. That's not fair to us, so I'm going to lower your salary. Therefore, a player could also do the same similar thing and be like, hey, I have these performance standards that are really high, and most every single person that has these performance standards are getting paid this certain high amount, so I should get paid this way. So the model deployment for this would help players and home teams and owners be able to more accurately negotiate between themselves on their salaries. So, in summary here, like I said, this is an evaluation of the Major League Baseball most cost-effective players of 2013 in order to predict the potential salary of a new or existing player in the MLB based on performance. All this is done through the auto model feature, which I use to make 5 different models, and through the use of different performance metrics like RMSE, correlation, relative error, R squared, MAE. It was made clear that the deep learning model was the best model for this data. However, it was not good for the data, but it was the best data, or it was the best model for this data. So, and we can specifically see this through certain numbers, like the relative error being the lowest at 52%, and the deep learning model had the highest correlation. Furthermore, it had a good R2 squared, R squared value of 77%, which I talked about just previously, and it had the lowest RMSE at 2.1 million, which is still not a good RMSE, but it was the lowest, so it was the best out of these models. Um, so basically, overall, we can see here that it does not do a good job of predicting a player's salary based upon their performance. So in order to predict salary more accurately, we'd need more different variables to use in this model. But one thing that we did learn through this model and that we definitely know for future models is high inputs that are weighted. We could see this through the weights. So through a future model, somebody might want to look at such things as home run, season, RBI, BB, and R as highly correlated with the output of salary. And then they will also know certain things like throws, SH league, and bats have no to little weight or significance on salary, so they don't have to measure those things. So even though these models didn't do a good job of predicting a salary, we were still led to the fact that these certain attributes do reveal or express that a high salary or low salary will be there or not. So we can see all this through the coefficients and p-values and weights like I had previously said from the model results. So some slight changes that could be made to the study that I think would get more favorable results for model implementation would be, maybe some more appropriate and observations for regression results. Add more variables that could be significant to salary. Make sure there's no omitted bias issues here. Make sure variables are not altered by human error when recorded. Find new ways to collect data more effectively and remove variables from the data, like I said, such as throws, SH league, and bats that have no weight or significance on salary to save time. And then I think the main thing we need here is to get more observations from different years. I think if we're able to look at this problem from a different timeline, from let's say 2010 to 2020, we'll get a much more accurate model that will be able to predict a player's salary based upon their performance. So overall, we know that although none of these models do a great job of predicting player performance, we know through this model deployment that certain things such as season, HR, RBI, and BB are good, and that this model is definitely going to need some tweaking if it's going to be implemented, but it definitely needs to be implemented for better negotiation between players and their owners. So thank you for your time today. Thank you for listening. Here's my references from Kaggle. I hope you enjoyed this presentation. Thank you.